Hi everyone, I'm Kim Heen. Today I'll present my Kaggle competition report on ASA rating prediction, a machine learning project where I used pre-operative clinical data to predict the ASA physical status class. Here is today's agenda. First, I'll introduce the overview and objective. Then I'll walk through data pre-processing, how I developed models, how I evaluated them, and I'll close with key conclusions. In the overview section, I focus on three things. 1. The objective and goal. 2. The causal relationship why these variables should predict ASA. And 3. The data distribution, so we understand what the model is learning. My overall objective is to apply machine learning algorithms to predict ASA physical status using a clinical dataset. I set two concrete goals. Goal 1 is to establish baselines using basic classification models, and Goal 2 is to apply stronger boosted tree models, specifically LightGBM and XGBoost. The target I predict is ASA Rater, which is a pre-anesthesia classification that summarizes a patient's overall systemic health before surgery. In the dataset, the labels only include ASA 1 to 4, so the model is trained to separate those levels of baseline severity rather than procedure difficulty. Clinically, this matters because ASA is strongly associated with perioperative risk stratification and resource planning. Here, I'm using a clinical decision-making framework with a causal diagram, also called a DAG, to clarify causality versus prediction for ASA. On the left, U is the patient's baseline health and comorbidities, which directly determines ASA. Baseline health also relates to surgery complexity, S, and S strongly constrains the anesthesia method, A. In real workflows, ASA assessment can also influence the anesthesia plan, so A often becomes a downstream proxy for severity and procedure requirements. That's why anesthesia method can improve ASA prediction, but it's not causal. We shouldn't interpret it as anesthesia causes ASA. For modeling, it's valid only if anesthesia method is known at prediction time, otherwise it can introduce leakage. ASA then serves as a risk stratifier linked to postoperative outcomes and mortality. So in this case, my scenario is the prediction moment that happened before anesthesia planning. All history features, prior surgery anesthesia catheter use, demographics, body habitus, medication history, and preoperative laboratory results are upstream proxies of baseline severity and acute status, which causally determine ASA. No current case planning variables are used. Anesthesia, method, catheter, use, and surgery, DAISHI, name, reflect prior clinical history. They are upstream proxies of baseline health and are valid pre-anesthesia predictors, because if they reflect the current case plan, they become downstream decisions and can leak ASA. This slide summarizes the dataset structure and missing data. Several variables have significant missing rates, for example, weight and lab values, and some semi-structured fields like catheter use and properties as display. This is precisely why my pre-processing pipeline emphasizes robust parsing, safe imputation, and consistent transformation across both train and test datasets. Here, I visualize distributions such as age and weight histograms and category splits such as gender and patient source. This step matters because the majority ASA classes can dominate model performance, so I always interpret results using both micrometrics for overall performance and macrometrics for fairness across classes. Now I'll summarize the data pre-processing and feature engineering I used to predict ASA rating, focusing on clinically grounded transformations and leakage control. From transform dataset handle missingness, inconsistent formats, applied TF-IDF experiments, unified pre-processing. Missing values are a big reason this pipeline works in clinical data, so I handled them in a way that's robust, leakage safe, and clinically reasonable. I first cleaned invalid placeholders and malformed empty text entries by converting them to NaN. For numeric features, I used median imputation, fitting the imputer only on the training data folds to avoid leakage. For categorical features, I filled missing values with an explicit missing category before encoding, because missingness itself can be informative in clinical data. I also captured missingness as signal indirectly using severity/burden features like total unsuture labs, total unsuture abnormal unsuture labs, high-risk med unsuture count, and device burden. Apply column alignment, re-index to both train and test to ensure consistent feature schema at inference. First, I standardized anthropometrics. Height had arrived as strings in mixed formats, so I parsed feet, inches, and converted everything into centimeters, and I converted weight to numeric. From height and weight, I computed BMI because BMI captures body habitus and is clinically relevant to perioperative risk and physiologic reserve. Second, I engineered severity signals from lab BUSTI values. This column contains multiple lab measurements embedded in text, so I did 3 steps. I normalized lab names using an alias dictionary, for example mapping calcium.ionized to calcium and urea nitrogen to bine, so the same lab doesn't appear under multiple names. I removed clearly invalid extremes values like 0.99 or 0 and treated them as missing. I parsed the text using regex to extract lab name, value pairs, and when multiple values existed for the same lab, I aggregated them into a single clinically meaningful summary. Then, instead of using averages, I computed a worst value per lab because ASA tends to align with the most severe physiologic derangement, not the mean. I used clinically directional rules. I took the maximum for markers where high values indicate worse status, like creatinine, BUN, glucose, INR, lactate, WBC, troponin. I took the minimum for markers where low values indicate worse status, like hemoglobin, hematocrit, albumin, platelets, calcium. For sodium, potassium, and pH, I used a stabilizing heuristic, the value closest to normal because both hypo and hyper states can be dangerous. Next, I reduced noise in surgery unsurgery name. Raw procedure names are very sparse text, so I mapped them into a small set of clinically relevant features. A risk tier, high, medium/low, using keyword triggers like cardiac, transplant, or thoracic, indicating higher risk, and an emergency flag using keywords such as emergency, rupture, bleeding, or trauma. This preserves the risk gradient while avoiding a huge vocabulary. For medication usage, I parsed safely using as.literal insert-eval, then created targeted clinical flags. Vasopressors, norepinephrine, vasopressin, dopamine, inflam, and anticoagulants, warfarin, heparin, enoxaparin. These act as strong proxies for comorbidities and instability, which are directly relevant to ASA. For catheter use, I extracted device markers that reflect acuity, flagging high risk when text indicated CVC, PICC, arterial line, or central access. In some variants, I also captured insertion attempts. Finally, I built composite indicators such as severe anemia or sepsis-like physiology from labs and meds, and I created aggregate scores like high-risk med unhapter count as the sum of high-risk medication flags and device OL burden, combining device markers with ICU status in one implementation. These are useful because ASA is fundamentally a measure of global burden, not a single lab abnormality. To keep everything consistent and avoid train-test mismatch, I wrapped pre-processing into a single function that encodes categorical variables like gender, ICUR patient, and patient underscores into numeric representations, generates all engineered features BMI, lab worst values, surgery risk tier, medication, and catheter flags, drops the original raw text columns after extraction, Hechelet, surgery, new, name, medication, usage, lab azir values, and catheter use, and finally aligns train test features using re-index columns, x-tolums, chi train tolums, fill unscalo value equals 0. This alignment step is critical in Kagge settings because train and test may contain slightly different observed patterns, and we need the same feature matrix structure for modeling. Beyond the rule-based extraction, I also ran TF-IDF vectorization on selected text fields like medication usage and properties play. Then I stacked TF-IDF sparse features with the structured numeric features using sparse H-stack. This adds flexibility and can capture extra signal, but it also increases dimensionality, which makes tuning more sensitive. After pre-processing, I trained baseline models, naive Bayes, logistic regression, decision tree, KNN, and SVM. I use stratified K-fold cross-validation so each fold preserves the ASA class distribution. These baselines act as sanity checks. If a baseline is strong, it tells me the engineered features already contain meaningful signal. Next, I trained LightGBM and XGBoost because ASA is driven by nonlinear interactions such as the combination of age, labs, high-risk meds, ICU status, and device burden. I tested both default and tuned variants, and I used early stopping where appropriate to reduce overfitting and speed up training. Here are the results for the basic models. Logistic regression performed best overall among the baselines, with microphone around 0.56 and macrophone around 0.49, indicating it generalizes well when features are clinically structured. KNN had decent microscores but weaker macroscores, suggesting it struggles more with minority classes. Nightbase performed poorly because its distribution and independence assumptions don't match these correlated clinical features. This table shows that boosted trees achieve the highest overall performance. Microphone rises to about 0.63064. However, macrophone improves only modestly, peaking around 0.496. That tells me boosting mainly improves performance on the majority classes, while minority class separation remains difficult likely because ASA boundaries between adjacent classes are clinically overlapping. In this project, my results show that ASA prediction is mainly a severity extraction problem rather than a purely algorithmic one. The largest performance gains were achieved by transforming noisy clinical text into structured, clinically meaningful features. Baseline algorithms were useful for sanity checks, and logistic regression performed best among the 5 basic ML algorithms because the engineered features already contained strong signals. However, ASA is driven by nonlinear interactions, so boosted tree models like LightGBM and XGBoost model evaluation show the boosted trees win on micro, but macro gains are modest. Tuning highlighted the expected trade-offs. Increasing depth or model flexibility can improve fit but raise overfitting risk, whereas smaller learning rates with more estimators generally improve stability at a higher compute cost. Missing value handling was also essential. Clinical data is missing not at random, so I treated invalid placeholders as NaN. Used median imputation for numeric features, and created an explicit missing category for categorical features. In conclusion, my system shows that predicting ASA reliably depends on clinically grounded pre-processing that transforms complex perioperative records into stable severity signals. Baseline benchmarking provided a performance reference, while boosted tree methods yielded the best results because they capture nonlinear acuity interactions. The final pipeline is robust, handles malformed text and missing data, interpretable, features reflect clinical reasoning, and free of data leakage, ensures consistent train/test processing. Future improvements should focus on strictly limiting feature discovery to training data, refining text representations, safer TF-IDF integration, using LOM as a feature generator, and enhancing performance for minority classes through calibration, cost-sensitive learning, or targeted feature engineering. Thank you for listening. This presentation was created using Canva and Resemble.ai.